looks good. All right, we are live. So, welcome everyone to Kopernik Observatory and Science Center. Welcome back, I should say, because we've been virtual for a bit. We did our virtual winter star party. Did anyone tune into that live stream? Oh, you got a couple people. Very good. You can actually go. You can actually go back on our YouTube channel and watch that if you'd like. The skies didn't hold up for us very well, but we have our opening remarks that you can watch. We have our main presentation that was really fun called "Who Says Astronomy Can't Be Funny," and we have an attempt to talk about the winter skies. Again, I said this, as I mentioned, the skies didn't hold up, but we worked with what we had. Tonight, though, did everyone get to see the moon? Just about everyone? Very good. Yeah, it cleared up. Like, the forecast was not looking great. And as you may know, there is a storm coming, too. a winter storm. So the next, 24 hours, we might get some snowfall. But right now, we have a nice clear view of Orion. We have a nice view of the moon. So hopefully you got to look through our telescopes. That's one of the rules at Kopernik. If if you visit us and the skies are clear, you got to look through a telescope. So make sure you do if you haven't already tonight. But the moon was our prime candidate for viewing through our scopes. If the skies are clear after the program, we'll see what else we can find. Any newcomers to Kopernik tonight? Raise your hand. Oh, welcome, Marcin. So I saw a couple hands go up though. If you are unfamiliar with Kopernik, you can of course learn more about us at Kopernik.org. We list all our public programs here, as well as we'll post our summer camps right at the top once we have those put together. So if you have a family that would be interested in taking a K through, I think it's K through 8 summer camp, you are welcome to visit the site, and you can also register online or over a paper form. We'll post more of our Friday night programs. We are going to have a public program every Friday night, unless something changes in our environment. We'll do a public program every night starting at 8 o'clock in the springtime, and we'll transition to earlier times in the summer. Okay, and then if you scroll down to the bottom, you'll also come across the clear sky chart. And this is why I wasn't super expecting the skies to clear up. So if you look at our clear sky chart, you have cloud cover, you have transparency and seeing. This is geared towards viewing at an observatory, viewing the night sky objects. And the cloud cover should not be white if you want to see anything. But it turns out this is a little wrong tonight. We actually do have some clearing. So this is a great place to go if you're trying to figure out, will it be clear at Kopernik tonight? Check our sky chart. All right. Well, with that said, our big presentation tonight is going to be on Pi, and that's coming. The Pi Day is coming up in just a few days now, March 14th. So we have a great presentation from Marcin Mazur, a professor of mathematics at Binghamton University. So at this point, I think I will leave it to you.
Okay, thank you. Welcome everyone in this evening time. I'm very happy to see that people actually may be interested in things like that. So I just want to make it clear, this talk will not be where is pi, but what is pi. So, and maybe also some warning, there will be an explicit math language in this talk. So, but hopefully, at the end, I hope the talk about pi will be just a piece of cake for you. So, with saying that, let's start with a kind of little cartoon. And what are we supposed to talk about today? I guess he's looking for this, and this is the pi. So what is pi? Well, a simple answer. Pi is just one of the letters of the Greek alphabet, of course, but it's a symbol of something. What is it symbol for? That number. And this could be the end of the talk, but this is just the beginning. So I want to put some perspective, some historical maybe account of what it means and why do we care and how this came up. So to start, we have to just, go back and look at the development of the civilization, where when various civilizations, when they settled down and started to develop and build, there was a big need of accounting, dividing the land, counting how many grain they have, how much material they need to build. So this, of course, required some kind of tool to account for all this, and this is how, in some kind of empirical way, mathematics was slowly developing. And the first of those civilizations was a civilization of the Babylonians in ancient Mesopotamia, and it already started about 4,000 years BC, and they developed a quite sophisticated way of counting, a number system, and also of measuring things. So, for kind of completely empirical reasons, they realized that you have some curved maybe objects, and you can make sense of what the length is. It's easy. Take a rope, go along with it, and straighten up the rope, and measure it or assign a number to it. So we kind of assign a number which tells us how long something is. Similarly, at some point, people realized you can take a piece of land, an area, and again measure it, assign a number to it. And it's already, we all do that, but if you start thinking about it, it's completely not obvious why it works. Why area as a number makes sense. It should have this property that if you divide it into pieces, then the whole area is the sum of the pieces. But there's many ways of dividing things into pieces. Why would always the addition lead to the same number? It's actually quite tricky, but nobody cared that much. It worked. It allowed life to go on. So it was used pretty much in ancient Babylonia. Similarly, the Egyptians also developed mathematics to deal with measurements. And the mathematics of the Egyptians was not maybe as sophisticated as the Babylonian one. And we know quite a bit about the Babylonian mathematics because they had their schooling and writing on clay tablets. And these clay tablets were, dried, and they are very resilient. So many of them survived until now, and we can see actually, what type of science and mathematics and accounting they have been doing many, many thousands years ago. But the real change came through the Greeks. About 600 to 200 BC, there was a flourishing Greek civilization, and they actually developed the philosophical and also kind of basic rules for modern science. So everything, the way the science is built nowadays comes from the Greeks. And they, for the first time, didn't just do an empirical kind of discovery, but they wanted to know why. And then they realized you can build this abstract kind of ideal world of mathematics in which you can do deduction, deduce new facts from old facts, and then apply it back to real life and then do something useful with it. Many of the Greeks didn't care about the useful part. They just liked the ideal world and playing in their heads with it. And in particular, we have these measurements about length, area, and volume. And at some point, it's probably quite easy to believe that if you have a rectangle with sides A and B, you all remember from school, the area is A times B. So let's assume that. And then the question is, how about the triangle? What is the area of a triangle? And maybe some of you still remember from school, 1/2 times the base and times the altitude. So why is that? It's actually quite simple to understand that. The problem with ways of, some ways math is taught these days is that you are told without really understanding why things hold. This is completely not Greek. Greeks wanted to understand and deduce things. So let's look at the triangle. take the line through the midpoints of the sides, and let's do this little rectangle here, and then it's easy to see that this part and this part are the same. It's like, you know, you can make it out of wood and then just rotate this triangle and it will go down here, and the same thing, rotate this little triangle and go there. So you see that this triangle in area should be the same as this rectangle. But the rectangle has one side which is the base of the triangle, and the second side is just half of the height. So if you believe that, then the area of a triangle should be the base times half of the height, and that's it. So this is kind of how the Greeks would explain why this is the right formula. And then, of course, we have some polygonal regions, and you would like to understand the area. Well, it's easy. You divide it into triangles. You know how to do what to do with triangles. Then you add up, and you get the area of polygons. And then the Greeks wanted to have, they were kind of very fond of compass and ruler constructions. And they designed this concept, quadrature of a figure. You have some kind of plane figure, and the quadrature of this figure means a compass and ruler construction of a square with the same area. So quadrature is the same as squaring. This is when you say, you know, squaring a circle. Originally, this would mean using compass and a ruler construct a square whose area is the same as the area of a given circle. So the Greeks developed various techniques of quadrature. So here's the first fact, which goes back to Euclid. It was, well, you know, I'm not sure how much of this is still taught, but Euclid wrote a great text on geometry and mathematics at the time, and it became the main text until probably the middle of 1800s, when people started to write, you know, books better than Euclid's book. You can argue with that, but he was the main source of knowledge, of mathematical knowledge, for many centuries. And one of the facts he kind of observes there is the following. Suppose that you would like to square a rectangle. So you want to construct a square whose area is the same as the area of this rectangle. So what do? The Euclid says, take this line, to pick a point here. On one side, put the length A. On the other side, put the length B. Then draw this perpendicular line to the line where A and B are, and then take the semicircle with diameter equal to A plus B. And then let's see where these two intersect. They intersect at this point, and Euclid says the length you get here is exactly square root of AB. So in other words, square on this line is the same as rectangle on A and B. And you can do it with compass and a circle very easily. Second result, which is kind of older, we call it the Pythagoras theorem, but actually the Babylonians already knew that, is the following one. From school you may remember, you have a right angle triangle with, say, it's ABC, then A squared plus B squared equals C squared. For Greeks, the meaning was slightly different. The meaning was, if I take a square on A and a square on B and add them together, I get a square on C. So this means if I take two squares, I can combine them into one square. So this is again a squaring of the area of two squares into one square. So using this technique, you can square any polygon you like. But then the Greeks said, of course, the most beautiful, symmetric, ideal figure is a circle. Can we square a circle? I give you a circle, so you have the radius and the center. Is there a construction using a compass and a ruler of a square whose area is exactly the same as the area of the circle? And this became one of the three so-called problems of antiquity, which solutions were nobody was able to get a solution to that. There were many people trying to come up with constructions. There was always a mistake somewhere there. And we'll learn later what's the kind of answer to this desire or this problem. So let's move with that. So if you look at the circle, the Greeks already realized that all circles have the same shape. They are kind of rescaled versions of each other. So our universe has this nice feature that you can rescale everything, blow up every dimension, and then the lengths blow up by the constant, and the area by the square of the constant, and so on. So from that, you easily observe that if you take a circumference, which is just the length of the perimeter of the circle, to the diameter will always be the same, no matter what circle you take, because they will rescale the same way. When you divide them, the rescaling factor goes away. So this is a universal kind of constant telling you what is the ratio of circumference to the diameter of the circle. Likewise, you can do the same thing with areas. You can say, let's compare the area of a circle to the area of the square on the radius. So I'm dividing area of the circle by r squared, which is the area of the square with side r. And again, no matter which circle you take, this will be the same ratio, because the way the rescaling works. But it was Archimedes, one of those Greeks, around 250 BC, he proved that these two ratios are actually the same. The ratio of the circumference to the diameter, which is kind of about length, is the same as the ratio of the area of the circle to the square on the radius. So these are both the same, and the same for all the circles. And this, nowadays, this value, this ratio, two ratios which are the same, we denote it by pi. But again, the Greeks didn't denote it by pi, and we'll get to that sometime later. So how did Archimedes came to this realization that they are the same? And Archimedes stated his result as follows. So let's see what we are saying. Since these two ratios are the same and equal to pi, circumference is just 2 pi times r, the thing you remember from school, and area will be pi r squared. What is pi r squared? You can write it differently. It's a half of circumference, which is pi r, times another r. This is pi r squared. So Archimedes stated his observation completely differently. The Greeks didn't really had algebra, and they didn't use really numbers. They used the concept of area, and Archimedes would say the circle on radius r is equal to the right-angled triangle whose one arm is the circumference and the other is the radius. You see, what is the area of a triangle? It's 1/2, one arm, which is the height, and the base, which is the other. So this is exactly the same thing, but described completely geometrically. He was, one of the most ingenious people in history, and in particular, he discovered this nice observation. How did he get to that? It's quite simple, actually. So this goes back to this observation that whenever you have a circle, you can both inscribed and circumscribed regular polygons. So on this picture, you have a hexagon, 6 sides, but you can do 10 sides or 20 sides or as many sides as you want. They are all of equal length, and they are either tangent to the circle, the circumscribed one, or the inscribed one has all its vertices on the circle. Very good, but let's focus on the circumscribed one. And the Greeks realized and actually proved that if the side is bigger and bigger and bigger, then the difference between the circle and the polygon is less and less and less important, goes to 0, in other words. So you get a better approximation. So let's believe that for a moment. So you suppose that you have this n-gon, regular n-gon, circumscribed on a circle. So you divide it into n identical triangles. One vertex is in the center, and the other two form one of the sides. What's the area of a triangle like that? Well, what's the height? The radius. And what's the base? the side of the polygon. So the area of a triangle is 1/2 A times R. And how many such triangles do we have? N. So the total area of the polygon is 1/2 times NA times R. But what is NA? If I add A to itself n times, I get, well, that's right, but geometry, what it means. If you add all these sides, you get perimeter of the polygon. So you can write it as 1/2 perimeter times R. So the area of the polygon circumscribed is just 1/2 the perimeter of the polygon times the radius. And now when n becomes huge, the perimeter of the polygon becomes more or less circumference of the circle. So when letting n to be bigger and bigger, you see, and this becomes the area of the circle. So nowadays we say when n tends to infinity, the area of the n-gon approaches the area of the circle, the perimeter of the n-gon approaches the circumference of the circle, and you therefore get that the area equals 1/2 times the circumference times the radius. And that's it. So we did 2 proofs already here. And again, the Greeks proved more precisely the fact that this actually really approximates the circle when n goes to infinity. The actual difference between the polygon and the circle becomes arbitrarily small. So let's wrap it up. So we are considering the circle of radius 1, and we'll be looking at perimeter of inscribed regular n-gon, and I will call it IPN. So this is when you add all the sides of the one inside the circle. And CPN means perimeter of the circumscribed regular n-gon. So I and C, of course, is inscribed and circumscribed, and P is for perimeter. And then the same with area. So IAN is the area of the inscribed regular n-gon, and CAN is the area of circumscribed regular n-gon. And the Greeks observed that the inscribed perimeter always is a little less than 2 pi, the circumference. Remember, the radius is 1. And it's a little bit, and 2 pi is a little bit smaller than the perimeter of the circumscribed one. And same with the areas. And more precisely, when n grows, the inscribed perimeters grow and never exceed 2 pi, and the circumscribed perimeters decrease and never go below 2 pi. And the same thing with areas. So, and the difference, if n grows, the difference of the outside and the inside becomes as small as you want. So in particular, if you take very, very large n, the inscribed will give you a lower bound for 2 pi, and the circumscribed will give you a upper bound for 2 pi. So this is how the Greeks wanted to understand what this pi is. And let's see what happened. And maybe one more remark, it's a little bit of computation involved, that if AN is the side of the one inside, the side of the n-gon inscribed, then the circumscribed one has side equal to this strange number. It's not that important, but if you really want to kind of play with it a little bit more carefully, this is useful to know. So I'm just stating that for reference. So now the idea is, we will not work with every n. The idea is that we start with some basic one. Suppose that we start with a regular triangle, so trigon inscribed. And then we don't go to the 4-gon, we will go to 6-gon, in other words, hexagon. How? You see, we have these 3 sides, so we have 3 arcs. Now we take a midpoint of every arc and then join with the old vertices, and we double the number of vertices, and we get hexagon. Now, you have a hexagon, you have 6 arcs, take the midpoint of every of these 6 arcs, and start joining old vertex, midpoint, back to old vertex, midpoint, and so on. You again double the number of vertices, and you get 12-gon. and then you do the same, and each time you double the number of vertices, and you would like to compute what is the perimeter of that, and this should give you a closer and closer and closer value of the number pi. So now is the warning. There will be some math here, some very explicit math language. So let's analyze. So suppose that A is the site of the regular n-gon, and then we are doubling, so we're taking the midpoint of the arc, and then B will be the new one, the site of the 2n-gon. And we would like to understand how is B obtained from A. And it's not very difficult, but you may start feeling that you are back in school, playing with formulas. We will use Pythagoras theorem. Let's look at this right triangle. And I will call this side X. We don't know what it is, I will just give it a name. So the Pythagoras theorem says that the hypotenuse B squared is x squared plus half of A squared, which is this. And now I will look also at this right triangle. And again, Pythagoras says that the hypotenuse, which is 1, the radius of the circle, is equal to this part, which is 1 minus x, because the whole thing is 1. So if this is x, this is 1 minus x squared, plus a squared plus 4. And now, a small algebra, there is an algebraic trick how to square the difference of two numbers. It will be 1 minus 2x plus x squared. So this is the same as 1 minus x squared. And then finally, you still carry over the a squared plus 4. But now you observe that the last two things together is what this formula tells us about. So it's b squared. So I can substitute instead of this part b squared. And what do I see? The 1 cancels out. The 2x I can move on this side, and I see that 2x is b squared. In other words, x is b squared over 2. So now I plug in this x to this first formula, and I see that b squared is b to the 4 over 4 plus a squared over 4. And then I do a little bit of algebra. I will not maybe go too carefully over that. And I observe that 2 minus the b squared minus 2 squared is 4 minus a squared. I take square roots. And you can say, oh, you made a mistake. Because it's b squared minus 2, square root of b squared minus 2 should be b squared minus 2. And I wrote 2 minus b squared. But what's the problem? You see, a square root of something is always positive. And b squared is smaller than 2. So this is a negative number. So the square root will give you 2 minus b squared, not b squared minus 2. So you have to be careful when you do algebra. And then you compute finally what b is. So the upshot of all this is that we fully control the next side if we know the previous side. So if A is the side of an n-gon, then this will give you the side of a 2n-gon. And Archimedes actually started with a hexagon and divided 4 times to get to the 96-gon and did these computations and was able to show, without having any decimal system or any algebra, he only knew geometry. It's kind of amazing how he did that. But he was able to see that pi, the one we are interested in, is between 3 and 10 over 71 and 3 and 10 over 70. And if you do the decimal expansion, this one is more or less 3.1428, and the lower bound is 3.1408. So what did Archimedes do? Archimedes actually found the first 2 decimal digits of pi. We do not know what the third one is, because the lower bound and the upper bound don't tell us what is the third one, but 1,4 is the same, so this must be the correct first 2 decimal digits of pi, 3.14. So this is kind of amazing achievement. It was about 250 BC by a Greek who didn't have all the modern algebra and notation. And how he did it? Well, if you're curious, there is this very nice book, a series of books actually. They are called Great Books of the Western World, and the volume 11, I think, yes, is Euclid, Archimedes, Apollonius of Perga, and Nicomachus. And all the work of these great people are in this little book. And if you really want, you can just go on eBay and you can get it for about $11. Knowledge, worthless. Not worthless, what I'm saying. There's no money you can, translate into this knowledge in these books, of course. But nowadays, of course, books are not valued much. People move away from books. So if you have some interest, I strongly recommend looking at this book. And it's very nicely translated works of Euclid and Archimedes in particular, which explain how he carried over the computations to get this approximation. So I will do something a little bit different. Archimedes started with hexagon. I will start with a square. And remember, this is the formula. If I have a side an, if I divide and make 2n ogon, this will be the new side. So I will start with a square first. So what is the side of a square if the radius is 1? Well, let's look. It's 1, 1. It's a right angle triangle. So Pythagoras theorem will say that A4, the side of an inscribed square, is square root of 2. And now I want the 8, 8. So now I divide every arc in half and want to compute the new side. And this is the formula which tells me. So if I plug in for here square root of 2, if I square root of 2, what do I get? 2. 4 minus 2? 2. So I will get square root of 2 minus square root of 2. So this is my new A with 8 sides. Now I start with 8 sides, again divide everything in half, and then the 16 gon inscribed will have side. How do I get it? Again, I use this as my A, I square it, then take 4 minus, which will give me 2 plus square root of 2. Then I have to take the square root of that, and then 2 minus and square root. So the next one will be this one. And then you repeat the process. The 32 gon will have side obtained from the 16 gon using this formula, and you see that you just add another 2 there. And then another 2. So, you have 10 minutes, you can sit down and slowly do these computations, and you will see something amazing. There's a pattern, very clear pattern here. If you do it n times, what will you get? Square root of 2 minus, and then you stacking these square roots n minus 2 times. And this is just the formula. So this is just the side of a regular 2 to the n gon. The perimeter, you have to add them all. They are all equal, so you have to multiply by 2 to the n times the side. And this will approximate the circumference, 2 pi. So if you divide by 2, this number, 2 to the n minus 1 times the side, will be a good approximation of pi. So this is the inscribed one. If you repeat the same thing for the circumscribed, you have to trust me with that, you will get the following formula for the upper bound. And this is the same as here, but you have to divide by these iterated square roots. And these iterated square roots will become closer and closer and closer and closer to 2, actually. So 2 over that will be very, very close to 1. So the left-hand side and the right-hand side are very close to each other, and pi is squeezed in between. So now we reduced approximating pi of just computing square roots, multiple times various square roots. How to do that? It's another problem, but it seems much simpler problem than measuring a circle. And indeed, this can be carried over. Maybe for kind of aesthetic values, I will tell you that you can rewrite this slightly to the following formula for pi. Pi will be this infinite product. You take 2, you multiply by 2 divided by square root of 2, then you multiply by 2 divided by this 2 iterated square root of 2 plus square root of 2, and then you multiply by this number and multiply this number and so on. And the point is that the first 2 multiply to this, then if you multiply it by that, you get this, so you get this kind of consecutive approximations. They are closer and closer and closer to pi, and if you multiply it infinitely many times, you get pi. What does it mean? Well, that's a little bit tricky, and we'll get to that in a moment. But so this is due to actually to a French mathematician, Vieta, around 1580. He was carrying over the Archimedes work. He was actually able to, so maybe before I get to Vieta, let's go back in time a little bit. So this basic idea of Archimedes, how to approximate pi, now you need to actually do the computations and get the numbers. And there were many people doing that, but the first significant improvement actually comes from a different region, as a Chinese mathematician, whose name is written here. I'm not going to even try to pronounce it, but you can read it. It's about 500 AD, and he computed the first 6 decimal digits of pi. No computers, no calculators, but the Chinese had an advantage over the Greeks. The Chinese had the decimal system, as we do, and it was much easier for them to carry over computations. And he also found this very, very close approximation to pi, which gives you 6 decimal digits actually, with this simple fraction, 355 over 113. We have no clue how he came with that. It works, but his works didn't survive. We only know from later commentators that he had that, but we don't know how he arrived at that. So then the next one is the Vieta I mentioned before. Around 1580, he carried the computations to starting with hexagon and dividing 16 times. So there's 2 to the 16 is already a pretty big number if you think about it. Well, they didn't have TV at that time, so he was spending hours computing, and he got 9 decimal digits of the pi. Later, not that much later, 1610, another mathematician, Van Keulen, got 35 decimal digits because he did it 62 times. He divided by, multiplied the size 62 times. 2 to the 62 is a huge number. And then people started to think, are there any other methods to understand pi? And John Wallis was on the birth of calculus. He was one of the people who were kind of having good ideas towards calculus, and he, using completely different reasonings, proved that pi over 2 is another infinite product, but no square roots here. You take 2 squared and divide by 1 times 3. Then you take 4 squared and divide by 3 times 5. Then you take 6 times 6 divided by 5 times 7. Then 8 by 8 divided by 7 times 9. So I think the pattern is clear. And these ratios will be closer and closer to 1. And you start multiplying them. And if you keep doing that to infinity, at the end you get exactly pi over 2. But the message is, if I do it 10 times, then I should get something close to pi over 2. And if I do it 20 times, it will be even closer. And so on. But the real breakthrough came when calculus was discovered. Newton and Leibniz were the 2 people who created calculus. Of course, this is kind of, the statement you have to take carefully. There were many other people with similar ideas, but they made the breakthrough, and they are actually the ones we now credit with that. But there were many other contributors with good ideas. And calculus opened new methods to approximate pi. And Isaac Newton, one of the key creators of calculus, he computed pi to 16 decimal digits using his so-called binomial formula to expand square root of 1 minus x. I'm not going to explain what it means, but he said the following, and he never published that. He had his notebook with his discoveries, and this was discovered many, many decades after he actually did that, and then finally published. But he writes the following: I am ashamed to tell you how many places of figures I carried these computations, having no other business at that time. Thanks for not having internet or other things, because probably he wouldn't spend his time computing the digits of pi. But there is a better way. The other creator of calculus, Leibniz, and a little bit before him also a British guy, James Gregory, they found this amazing formula. I will first say what it is and then explain a little bit. So arctangent x is x minus x cubed over 3 plus x to the 5 over 5 minus x to the 7 over 7 plus, and so on. You have to, so calculus gives us a very good way of handling this kind of infinite times adding something or multiplying something. It provides a perfect sense for that. But what is arctangent x? It looks very it looks Greek to us probably. It should be. Well, the Greeks didn't discover trigonometry, but anyway, let's see. You take a right angle triangle, one side is 1, and the other is the x you are talking about. Now, take a circle with radius 1 and center in this vertex. And this circle intersects the hypotenuse somewhere. And you have an arc of the circle. And the length of this arc is actually the arctangent x. So this is a simple way of explaining. So arctangent x, giving a straight length x, produces the curved length arctangent x as an arc of this circle. So for example, if x is 1, then this is just half of the square. So this angle here will be 45 degrees. So this part will be 1/8 of the circle. Circle is 2 pi over 8 is the same as pi over 4. So arctangent 1 is pi over 4. And therefore you get this amazing formula. Pi over 4 is 1 minus 1/3 plus 1/5 minus 1 over 7 plus 1 over 9 and so on. So if you keep doing that many times, you will be closer and closer to pi over 4. Well, the problem is that it's not very efficient. It will take you forever to get even 5 decimal digits because this very slowly kind of approaches pi over 4. So this is not good. But you can do better. It's not hard to see that if you take instead of 1 over square root of 3, then arctangent will give you pi over 6. And then if you plug in 1 over square root of 3, 1 over square root of 3 is smaller than 1. So the bigger powers of it will be very tiny, will quickly become very small. So this will converge much faster, and you get this formula for pi over 6. You have to, you do some algebra and you get it. It's not worth spending time. It's still not that great. But then, mathematician John Marcin, or not sure how to pronounce his name, around 1706, discovered a rather amazing formula that pi is 16 times the arctangent on 1 over 5 minus 4 arctangent of 1 over 239. So now you can plug in 1/5 in this formula. It will converge very quickly because you will have, like, what is x to the 7? Is 1/5 to the 7. So it's 1 over 5 to the power 7, which is 5 times 5 times 5 times 5, 7 times. So it's very tiny. So each next step was just a little bit change to the previous one, and very quickly you get the actual approximation to pi. And this was carried over actually. About 150 years later, Thomas Clausen computed by hand 250 decimal digits using exactly this arctangent approach. And then, few decades later, William Shanks computed 707 decimal digits. Well, only 527 were correct. He made a mistake, which affected all the computations there. It took him over 15 years. So no, I am really impressed that he only made mistake at number 527. The first 527 of them are correct. And then, of course, there were others and so on, but the real breakthrough came in 1949 when US Army used an electronic machine called ENIAC, one of the first kind of computers, to make a mechanical computation of the same pi, and it took them only 70 hours of computations, and they got 2,000 235 decimal digits of pi. Well, so now pi, why do we call it pi? There's no good answer to that, except that the first person who was using symbol pi for what we call pi, for this number, was a not very well-known mathematician, William Jones, in 1706. But then, a very well-known mathematician, one of the biggest giants in mathematics, Leonhard Euler, adopted this notation, and from 1742 on, he was using it consistently in all his works. And of course, if Euler used it, everybody used it. So we really use pi because Euler decided to use pi. And Euler decided to use pi because maybe he's seen it somewhere earlier and said, that's a good idea. That's a good name. So it's fairly new. You see, the pi, the number itself, and the problem existed for many, many hundreds of years, but the notation is fairly new. Euler also found the following amazing formulas. If you add reciprocals of squares, so 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25, and so on, you will get at the end pi squared over 6. And then if you add fourth powers, so 1 over 1 to the 4, 1 over 2 to the 4, which is 16, 1 over 3 to the 4, which is 81, and so on, then you get pi to the 4 over 90. And in fact, if you get any, I think I should use 2n here. So there is a mistake here. It should be 2n, not n. Reciprocals of 2nth powers of consecutive integers, then you get some multiple of pi to the power 2n. And this is an explicit expression which becomes more and more complicated if n grows. Doesn't matter, it's just a very aesthetically, I think, pleasing observation, but it has important meaning for number theory, actually. And then, something more modern, Eugene Salamin and Richard Brandt in 1976, so fairly recently, came up with the following very amazing algorithm. You start with three numbers. A0 is 1, B0 is 1 over square root of 2, and S0 is 1/2. And then you iterate some computation. Suppose that you already know what is AN, BN, and SN. Then the next step for the next AK plus 1 will be just the arithmetic mean, AK plus BK over 2. And the next BK plus 1 will be just geometry, so-called geometric mean, in our square root of AK times BK. And then SK plus 1 will be given by this formula, where CK is just the difference of squares of these two things. Doesn't matter that much. And then finally, once you compute these numbers, you divide 2AK squared over SK. And then this is some kind of number. And the point is that this number pk very quickly approaches to pi. So if you do every iteration, you double the number of correct digits. So if you do 25 times these computations, if you compute p25, you will get 45 million decimal digits of pi correct. So this is, of course, you don't do it by hand. You do it by computers. In 1976, computers already were pretty well established, and they carried over these computations and computed about 45 million digits of pi. And now, the most modern breakthrough comes from these two brothers, David and Gregory Chudnovsky. In 1985, they came up with very strange formula. I'm not going even to try to read to you that. I only say this exclamation mark is called factorial, and like 3 factorial means 1 times 2 times 3. And 10 factorial means 1 times 2 times 3 times 4 times 5 times 6 up to 10. And so on. So these are huge numbers. And the upshot of this is that these numbers very, very quickly become very, very tiny. And they, having this amazing formula, which is kind of quite deep, and using pretty clever computations, of course, using computers, they actually lived in New York City and built several computers in their apartment, tiny apartment in New York City, and carried the computations. And by about 1994, they computed 4 billion digits of pi. using these ideas. And then the most current record I am aware of continuing these ideas is from August 14, 2021, when 62.8 trillion digits of pi was computed. And trillion is this number. A lot of zeros there, so it would take you a lot of paper to write down all these digits. But of course, they are all electronically stored now, so we don't need to waste paper. And people, why do we do that? It's fun for some people, but also there's still the question, is there any pattern for the digits of pi? And we have no clue. These computations do not tell us almost anything about what really pi is. We are just closer and closer approximating it. But very basic question is pi a fraction? A fraction means a ratio of two integers, 2/3 or 7/8 or like 231 of 133 or something like that. We know a very good approximation to pi like that. Is it actually equal to something of that sort? Well, this was open for many, many years, but in 1761, John Heinrich Lambert proved no. Pi is not a rational number. No fraction can describe exactly pi. Another question was, is pi algebraic number, so-called? This is a more technical concept. This means, can I find integers, a0, a1, an, such that if I take a0 plus a1 times pi plus a2 times pi square and so on up to n, I get 0. For example, if you take square root of 2, 2 times 1 minus 1 times square root of 2 squared is 0. So square root of 2 is an algebraic number, but very, very deep theorem from 1882 by Ferdinand Lindemann says no, pi is not an algebraic number. No matter how big n is, and no matter what integers a you take, this expression can never be 0. Pi cannot satisfy, the proper way of saying is pi cannot satisfy any polynomial equation with coefficients which are integers, whatever it means. But consequence of this result of Lindemann, finally, 1882, the Greeks posed the question around 300 BC, quadrature of the circle is not possible. Because if you can construct something, it has to be algebraic. It's another result. So the quadrature of we all know that because it's a common phrase now, you're trying to square a circle. In other words, you're trying to do something impossible. And we know that because Lindemann proved that you cannot square the circle. There's no construction using compass and ruler which builds a square of area equal to an area of a given circle. But we still don't know much about pi. For example, when you compute these decimal digits of pi, will you get infinitely often 0? Or maybe 1? Or 2? We have no knowledge of that for any of the digits. We don't know if every digit will appear infinitely many times. Maybe from some point only 2 and 3 will be appearing there. Nobody has a way of proving or disproving that. We believe, the common belief is that yes, every digit should appear infinitely often. And part of the reasons people do these computations, they want to analyze frequency of 8, frequency of 9, frequency of 2 as a digit of pi, and maybe conjecture something and maybe get some clue, but not much progress about that up till now. We don't know. There is another beautiful number, maybe you remember, e. It's the so-called base of the natural logarithm. We do not know if you add pi and e, is it a rational number or not? Is it a fraction? We don't know. We also do not know if you multiply them, if it's a rational number or not. But we do know that one of them is not a rational number. We don't know which one, though. And I think the common belief is that neither one is rational. But you see, mathematicians still cannot do many things we would like to do. But the politicians sometimes help with that. So maybe a funny story. There is something infamous, Indiana Pi Bill. It's bill number 246 from 1897. The sitting of the Indiana General Assembly proposed by Indiana physician Edward Goodwin and introduced in the House under the long title, A Bill for an Act Introducing a New Mathematical Truth and offered as a contribution to education to be used only by the state of Indiana, free of cost, by paying any royalties whatever on the same, provided it is accepted and adopted by the official action of the legislature of 1897. They always have this convoluted language in these bills. And let me give you some excerpt of the bill. The bill says, furthermore, it has revealed to the ratio of the chord an arc of 90 degrees, which is a 7 to 8, and also the ratio of the diagonal and one side of a square, which is as 10 to 7, disclosing the fourth important fact that the ratio of the diameter and circumference is as 5/4 to 4. Whatever it is, I will explain in a moment. And then there's another sentence. It has been found that the circular area is to the square on a line equal to the quadrant of the circumference as the area of an equilateral rectangle is to the square on one side. So this is an actual language from an actual bill by the Indiana legislature, 30 years ago about. In simple terms, the last assertion, this sentence here, says that the area of the circle is the same as that of square with the same perimeter. So the area of the circle is pi r squared. The perimeter of the circle is 2 pi r. So the square has a side 2 pi r over 4, and then you need to square it. If this was true, then the very simple arithmetic would say pi equals 4. The Bill of Indiana makes life much, much simpler. Pi equals 4. The first paragraph of the bill has some contradictory information. For example, it says the square root of 2 is 10 over 7, though already Greeks knew that square root of 2 is not a rational number, is not a fraction. And he also says that pi, contradictory to this part, is 4 over 1.25, which is 3.2. Anyway, let's look at the story, how it kind of progresses. The bill passed, actually, in the House on February 6, 1897, without a dissenting vote. As this debate concluded, there was a Purdue University professor, Waldo, who arrived in Indianapolis for his business, in other words, to secure the annual appreciation for the Indiana Academy of Sciences, and an assemblyman handed him this bill and offered to introduce him to this genius doctor who has these great discoveries, to which Waldo said, I'm declining. I already met as many crazy people as I care to. And he also started to talk to some of the Senate members, explaining to them that it's total nonsense, and at the same time some papers, even internationally, started to write how ridiculous Indiana Assembly is, trying to introduce a bill everybody knows is false. So the bill went to be considered by the Senate, where it actually had been nearly passed. But at some point, influenced by this mathematician, opinion changed when one of the senators observed that the General Assembly lacked the power to define mathematical truth. And they didn't abandon the bill, they just tabled it indefinitely. So it's still tabled there, and it's one of the laughing points of, legislature in Indiana trying to, make a new law for what pi should be. Anyway, let me finish the talk. So over the years, of course, there is this little game of trying to memorize as many digits of pi as possible. I mean, it's kind of pointless exercise, except that you train your memory. But to aid with that, people discover various poems which kind of give you the digits. So here is one of them. You count how many letters every word has, and these are the consecutive digits of pi. So it says, how I want a drink, alcoholic of course, after the heavy lectures involving quantum mechanics. all of thy geometry, Herr Planck, is fairly hard. If you count, so 3, 1, 4, 1, 3, 1, 4, 1. So if you, every word, the number of letters will give you the next digit of pi. So this is one way of trying to remember the digits of pi. Why? I don't know. But this is a small introduction explanation for this great day we will be having on Monday. I hope instead of trying to compute more digits, you will just bake a good piece of pie and enjoy it. And let me finish this talk by that. So.
So, with the computers that are now making these very long calculations,
yes.
How do we know they're right?
Well, that's a very good question. But I think we don't, because there may be a little mistake in a chip, or we just believe that it's right, and people try to replicate it, but we don't. You see, this is why mathematicians don't try computers. Mathematicians don't accept computer-assisted proofs. They use it to guide them, but they only trust if they can prove something. Of course, this is beyond any human ability to compute it by hand. But yeah, that's a good point. We don't know. We know that the mathematics leading to these computations is correct. But every computation accumulates some error. There is a tricky point of assessing how much error you make, so you may be sure that first 7 billion million digits is correct. It's quite tricky, but believing that our world works, the plane fly, the banking system works, the computers don't make too many mistakes. So that's the answer, I guess.
All right, any other questions?
Yeah, I majored in chemistry, and pi kept on showing up in a lot of places where there weren't any circles.
That's right, because pi also shows in these other formulas which are related to other areas. So this is the amazing thing, that once the calculus was discovered, pi actually is showing up in a lot of integrations, which somehow are related to circles, but not in a transparent way. And of course, pi also shows in the volumes. Already Archimedes proved that to compute the volume of a sphere, of a ball, you need a pi. And also the circumference of the ball, the area of the ball, you need a pi. And there are many, many other places where pi shows less or more explicitly. Sometimes the relation to circle is much more tricky, but I think it's through various functions which are related to this, like the arctangent function. It comes from the circle at the beginning, but it actually is appearing in many other areas because it's an integral of a very simple function. So for those of you who may be still remembering, there is something which is called integral, which basically computes, if you know a velocity of something, the integral computes how much distance you travel after a given time. And the arctangent function is an integral of a very simple velocity, 1 over 1 plus time squared. So in many computations like that, then pi will naturally show up, and tons of computations of this sort are done in physics and chemistry and other areas. So yes, yeah.
So pi shows up in Euler's buckling equation as well.
Oh yeah.
Basically, tells us when a column will fail under a certain load.
That's right. But of course,
do in the circle.
Well, I think it does, because it has to do something with trigonometry. And trigonometry has something to do with the circle. So yeah, these connections are kind of multi-step, but at the end, but you're right. Nowadays, pi would take a transparent role, not because of the circle, but because it appears in all these other formulas and functions which are important in science nowadays, right? But, the development of the science was as it was, and the Greeks started with questions, and we wanted to answer the questions, and because of that, we developed the science. I mean, it's amazing, people, for no apparent good reasons, try to answer these silly questions or try to compute the hundreds of thousands of digits, And sometimes doing that, they stumble upon some new discovery, which actually matters, and then, leads to discovery of things useful for most of us. So this is how science works. Scientists often do science with no good reasons, except to have, pleasure out of it. But it also is applicable. And every now and then, these applications change lives of all of us really profoundly. So this is kind of amazing.
Any other questions from the audience here in person? All right, I actually do have a couple on the live stream. Let's see, from Dr. Gaidosh, or we call him Dr. Danger here at Kopernik. He's one of our educators and also former Binghamton University professor. He asks a couple questions. First, are there problems that cannot be solved, even theoretically, in mathematics?
Oh yeah, I mean, we just had them here. If you ask, will digit 7 appear infinitely often in the decimal expansion of pi? We do not know. Or is pi plus e a rational number? We do not know. And many, many questions like that. Yes, I think every time you learn something, you also learn that you don't know 3 other new things. And so, in other words, with every answer to a question, you get 3 new questions. This is how the life works.
Yeah, actually, his follow-up was, just asking, could it be proved that pi is irrational, which we did.
Oh, this was proved, actually. This is known from 1761, I think, and famous result from Lambert that pi is not a rational number.
All right. Well, that's what I have from the live stream. Any final questions here? All right. Well, thank you so much, Dr. Mazur. I did want to mention, too, on our Facebook page, we posted an interesting little article from NASA.gov where you can learn about how all the different ways, I think it was a student project, in fact, all the different ways that NASA has used pi in their space exploration. That's just obviously one small, narrow area where pi is used throughout all of STEM. So go check that out on our Facebook page if you follow us there, or follow us if you don't already.
So maybe I mentioned that the Indiana bill claimed pi to be 3.2, which is a bit bigger than 3.14. And the doctor claimed this will give add significant amount of space to the area of the Earth. So in other words, he said, we will have this undiscovered lands because the pi is bigger than people thought. So that's right.
Welcome everybody. Well, welcome. Say hello. I apologize for being late. I had another commitment earlier in the evening, but there is occasional holes in the sky, and so if you haven't already seen it, we can at least get you to see the moon, maybe possibly the Orion Nebula if it pops out. So the rule here is you can't leave Kopernik until you look through a telescope, and we'll lock the doors until then. So, we invite you to if you got other questions for Dr. Mazur, please go ahead and come on up. But otherwise, invite you out to the scopes, and we'll see what we can do to get you going. All right, thanks. How you doing, Andrew? Good to see you.
And those on the live stream, thanks for tuning in. We will see you next time.